Buildings are responsible for 40% of the world's carbon emissions. Every year, millions of tons of building and demolition waste go to landfills and are replaced with carbon-emitting materials. The area of all buildings worldwide is expected to double by 2060. By that time, as many as 200 million people may be displaced by climatic events directly attributed to anthropogenic climate change alone. Building for these climate refugees with current construction methods will only exacerbate the problems that displace them to begin with. How can we leverage the building process to reduce greenhouse gases instead of the current paradigm of emitting them? Many believe there is a biomaterial revolution coming that could flip the building industry from a problem industry to a resource for decarbonizing the atmosphere. Biomaterials are materials that use the growth of organisms in their manufacture. The term biomaterial can be differentiated from the term biomaterial, as biomaterials are commonly regarded as materials that work well with biology, which includes inert materials like titanium used in surgeries. Biomaterials can also be differentiated from bio-based materials that are derived from living organisms, usually harvested at the end of their life, and then converted to usable material. Think here of wood from trees that have grown for decades and then are processed into materials. Even plastic can be considered bio-based, as the fossil fuels used to create plastics are from organic sources. Biomaterials are something different. The organisms are grown as part of the process of making the material. There are currently several ways of leveraging biological growth to make materials, and we expect there will be hundreds more by mid-century. Many of these processes can absorb carbon dioxide, and by turning them into materials that can be locked away in buildings for decades or centuries, that carbon dioxide is kept from returning to the atmosphere. Biomaterials include materials made from microorganisms like bacteria, cyanobacteria, and fungi. Calcite is the most common form of calcium carbonate, a material that makes up about 4% of the rock on Earth. Just as coral use calcium carbonate to build structures in nature, so may bacteria. And just as nature forms rocks like limestone, so may we, when we leverage the process to bind aggregates like sand and gravel. Bacteria secrete calcite as the byproduct of their digestion, so all they need are the conditions to thrive and multiply. Nutrients, proper climate, gas exchange, and a competitor-free environment. Biomason is a company that is commercializing bricks from this process. They replace cement, a huge emitter of carbon, with calcite that pulls carbon out of the atmosphere to make the bricks. Cyanobacteria, or blue-green algae, are photosynthetic bacteria. Maybe you've had this in your health drinks as spirulina or chlorella. As with any photosynthetic organism, cyanobacteria convert carbon dioxide into carbon-rich biomass and release oxygen. Many researchers are growing algae in labs to create plastic alternatives. This alternative plastic replaces fossil fuel-based substrates that create disposal nightmares with carbon-absorbing substrates that can compost naturally. Algal plastics can be 3D printed, can be made to replace disposable products like shopping bags, and may one day replace building components that are made from fossil fuels. A SCOBY is a symbiotic culture of bacteria and yeast. It's what brewers use to manufacture kombucha. In kombucha, bacteria and yeast grow together, metabolizing sugar into alcohol that gives kombucha its vinegary taste. There are many different ways to produce these symbiotic cultures, and many uses for them, alive or dead. The living symbiotic organism is sometimes used as bandages for burns, where the moist culture nourishes the wound. The cultures can also be dried and turned into vegan leather or parchment. Imagine the possibilities when leather can be produced in short order without harming animals, and the byproduct is alcohol. Mycotexture is the shaping of the built environment using fungal mycelium, the root-like branching hyphae of fungi. In 2009, Phil Ross, an artist and entrepreneur in California, built a tea house in a German gallery that was made of living blocks of reishi mycelium. The mycelium had fruiting mushrooms that could be harvested directly from the structure and made into tea. Ross would later go on to found MycoWorks, a leader in mycelium leather. In 2014, David Benjamin, an architect and professor at Columbia University, designed a structure made of mycelium bricks for MoMA's PS1 gallery in Queens, New York. The blocks were made by Ecovative Design, who make packaging materials from mycelium and agro-waste that can replace styrofoam packaging. Mycomaterials can be soft and spongy, can be elastic like leather, they can be insulative, and they can be structural. In the future, we expect they could be self-assembling, self-cleaning, self-repairing, bioluminescent, and may even be able to alert us to pathogens like viruses in our environment. NASA is currently funding a study headed by astrobiologist Dr. Lynn Rothschild to develop self-assembling off-planet structures that use fungal mycelium to produce radiation-attenuating biochemicals in situ. The structures would use autotrophs grown at destination with locally sourced water and nutrients, saving NASA billions in transport costs. Mycelium will grow through the algal biomass to create a composite that is structural, insulative, and protective of micrometeorites and cosmic radiation. BioHab is a project that looks to bring this technology back to Earth using some of the same engineers and components, such as inflatable formwork. BioHab converts Namibian encroacher bush into food and building materials while storing captured carbon. The Acacia mellifera, or encroacher bush, has proliferated ever since European settlers changed the natural migration patterns to secure cattle farms. The proliferation of this bush is the first step in the process that would change the grasslands into a barren desert. To combat this desertification, the Namibian government is promoting bush thinning that extracts only the excess amount of acacia. This has led to a great amount of sustainably harvested biomass. There is roughly 330 million tons of biomass in Namibia that can be sustainably harvested every 15 years, according to the Namibian Ministry of Agriculture. So here is a bush that captures carbon and needs to be extracted. What you do with the carbon once it's extracted falls into two categories: carbon capture and utilization, CCU, or carbon capture and storage, CCS. CCU often re-emits the carbon into the atmosphere and is sometimes considered net zero carbon. CCS stores the carbon either underground or in a product that does not degrade into the atmosphere. In the example of the encroacher bush, parts of the biomass could be used for cattle feed, and parts can be used to create charcoal or fuel pellets for energy and heat. While burning or metabolizing the carbon-rich material releases carbon dioxide, these uses are considerably more ecologically friendly than the alternatives and can create net zero energy and sustainable animal fodder. However, if that biomass could be locked away instead of emitted, we could actually leverage industries to keep carbon dioxide out of the atmosphere. By putting this wood mass into buildings, BioHab does exactly that. In this process, BioHab takes the extracted bush, grinds it into small bits, pasteurizes it to kill the microorganisms living in the dust, and feeds it mycelium, which will grow mushrooms and create strong multifunctional composites that can be pressed into blocks or panels. From the architectural point of view, mushrooms are the byproduct. For the food insecure, it is of course the main objective. At the BioHab site, oyster mushrooms are grown in shipping containers. The average growth time is about 4 weeks, a much shorter period than most crops. Oyster mushrooms produce more protein per liter of water than any meat, and in a desert like Namibia, that matters. Once the mushrooms are harvested, the biocomposite of mycelium and encroacher bush are loaded into a press and compacted into a dense, interwoven matrix of lignocellulose and chitin, two very strong natural compounds. The material is forced into a metal mold and baked in an oven at low temperatures to dehydrate. Once extracted, the blocks weigh about the same as standard concrete blocks and are just as strong in compression. As Penda is demonstrating here, they have a much better impact resistance. Where they differ from concrete is that they are net carbon stores and, owing to their volume, are insulative. The calculation of the carbon storage of these 10-kilogram blocks are as follows. Each block is 60% carbon as defined by lab procedures, meaning that 6 kilograms of the block is carbon. That carbon was made from converting carbon dioxide into carbon and oxygen, and as carbon dioxide is a much larger molecule, a conversion factor of 3.67 is used to create a 22 kilogram carbon dioxide equivalent. As stated earlier, there is 330 million tons of biomass that is naturally replenished every 15 years in Namibia. If we were to take about 1% of that and convert it into food and housing using BioHab's processes, we would have enough food to feed millions and export for profit to subsidize the housing of Namibia's 500,000 unhoused people. Here's the math on that. Namibia has 330 million tons of biomass that can be sustainably harvested every 15 years. If BioHab uses 0.7% of that, we can turn that 2 million tons of biomass into 2 million tons of mushrooms and 2 million tons of block. That's not magic. It's a concept called biological efficiency that converts biomass, water, and air into biomass and food. 2 million tons of block can create 125,000 homes that can house Namibia's 500,000 people currently living without dignified housing. That 2 million tons also translates to 4.4 million tons of carbon dioxide equivalent. The construction of the BioHab is very simple and works like this. An inflatable arch formwork is erected. The blocks from the cultivation waste are stacked on top. Once the myco blocks are in place as an arch, the formwork is deflated and can be used again and again. A mudlime rendering is added to protect the blocks from the elements, and a roof is added on top. Hi, my name is Chris Maurer, and I'm an architect and founder of Redhouse Studio based here in Cleveland, Ohio. Together with a group at MIT called the Center for Bits and Atoms and Africa's largest bank, the Standard Bank Group, we've started a company called BioHab that takes Namibian encroacher bush and turns it into food and building materials. You'll see footage of us in Africa growing oyster mushrooms and taking the waste from that to create large blocks like the one you see here. But since we're here in Cleveland, we're going to show you the process using reishi mushrooms, and the waste material from that, the mycelium, can be turned into smaller objects like the block you see here. So today's demonstration will be a little bit more accessible, and you'll learn about how to utilize mushroom waste yourself. So let's take a tour of the workshop. We'll see how we grow mushrooms, and then we'll come back here and utilize the waste material. So Haley and Armando are removing the cover from our steamer. This is where we pasteurize the bags of material. The steamer is made with a heating element that's underneath there that heats up water, and the water fills this area. It's held down with ratchet straps, which actually keeps it a little bit pressurized. Sometimes it gets a little bit above 212 degrees Fahrenheit, which means there's a mild bit of pressure in there. But that's what it takes to pasteurize the organisms. If it was to go all the way to sterilizing the substrate, it would have to be in a pressure vessel about 250 degrees Fahrenheit, or about 15 psi. You can see they've been in here for about 24 hours. They cooked at a temperature of 212 degrees Fahrenheit, 100 degrees Celsius, and that's what pasteurizes the material. It kills all of the organisms that are growing in the material inside of those bags. So we'll unload the steamer. We'll put that onto a cart and take that into our lab. And it'll cool overnight, so that way it gets down to room temperatures that we can introduce the mycelium. First thing to do is to clean the environment by spraying down the laminar flow hood and cleaning the adjacent spaces. Then we check the temperature of the bulk substrate to make sure it is cooled down enough from the pasteurization, and make sure all the objects we're using are clean as well. The bulk substrate can be opened up on the laminar flow hood. This has HEPA filtered air that is passing over the work surface so that no contaminants are in the immediate vicinity of the work surface. Then we add the grain spawn. This can be purchased from a grain spawn supplier, or it can be made in-house using mycelium on agar plates added to sterilized grain. After the grain spawn is added, we shake it up well, compact it a little bit, and then seal up the bag. All of the moisture, all of the nutrients are locked inside the bag, and it will stay this way until the mushrooms are nearly fully formed. From the biolab, Armando and Haley are moving the inoculated bags into the colonization room. So in here, the mycelium will run through the material, and then once it's fully colonized, we'll move it into a special fruiting chamber that has higher humidity, where we can open up the bags and they can be exposed to more oxygen. This room will remain dark for the next couple weeks, and those bags will fully myceliate. Here we are inside of one of our colonization tents, and this is where the substrate is brought in and starts to grow the mycelium on the bulk substrate. Here you can see some mycelium leaping off the spawn onto the bulk substrate, which here is sawdust, and you can kind of see that starting to form there. After a week or so, it'll look a little bit more like this, where all of the area starting to colonize, and you're seeing more and more large white patches. That's where the mycelium is starting to concentrate. And then after a week or so, you'll have material like this, where the primordia is starting to show itself, which are these very small mushrooms. Once the mushrooms turn into these larger primordia like this, it's taken into a fruiting room, which allows us to open up the bag a little bit to get some more oxygen in there, and we have a higher humidity environment for that to grow and to produce the mushrooms. Hey, so we're back now. Now that we've learned how to grow mushrooms, what we're gonna do is take the waste material from that, the mycelium that's binding together the woody substrate, and we're going to take that, we're going to blend it, and we're going to turn it into any object. So we can make any kind of form, and we can fill that form, and then it'll grow into that form and become a new object. So again, the waste material from the mushroom farming is what we're using to make these objects. We start by selecting one that is fully fruited. We're gonna harvest the mushrooms. So we'll take this and we'll put this through the saw, take the top off of this so we have our mushrooms that we can harvest later. And then the waste material from this, which is the mycelium, will be put into the blender, mixed up, and then we'll put that into a receptacle that we make using our vacuum former. So Haley and Armando are rolling in the bandsaw now. We're gonna select a mushroom that's ready to harvest, and we'll take off the top part of that. The mushrooms can then be used to make tea. Throw them in our blender. And where the rest of the product we will chip up and turn into new materials. So we'll just put that on the shelf for later. And then the waste material from this, so you can see, is sawdust that's held together with mycelium. So we'll take that, we'll start to take it apart, using gloves of course, and we'll put that into our blender here. So if it's less myceliated, you can use things like a concrete mixer. You can just break it up by hand as you see me doing here. But when the mycelium is fully colonnaded like that, it's a good idea to put it into the blender and chip it up so you have smaller material that you can work with. And you can see from where the cut was, kind of created a clean cut, but inside here you can see the matrix of material that is the mycelium and the wood mass all together. Got it set on smoothie. Okay, so you can see now this material is all chipped up. So you can see now it's all chipped up and real easy to work with. And now all we need is a receptacle to grow this in. You could use a container like this, and that's exactly how it would form. But what we're gonna do is we're gonna pull in the vacuum former and create a shape that we've made that we can replicate over and over again. First the vacuum, then our vacuum former. This is gonna require a little bit of setup. But what we're gonna do is we're gonna take these acrylic sheets and they're going to go in this frame here. The frame is going to be lifted up here, and there's heating elements there that's going to heat this material. And then once it starts to sag, you can tell that it's hot enough to be delivered down to the vacuum table. And then whatever object you put on top of that vacuum table, this is going to form around it, you know, within reason. So there are certain things you have to look for to create the form. But what we're going to do is use this wooden block here, and we're going to create a shape that is this trapezoid here that can tessellate. So this will be a good example of a wall tile you can make, and we'll make several of these so that way when we put them together they'll tessellate into a pattern, and we'll be able to change the characteristics of some of the materials to actually make it an interesting pattern. So there are many containers that you can fill this in. So you can get just normal Tupperware containers. You can use wooden containers that are lined with plastic. It's very important that whatever container you use, it's hydrophobic, that it's something that the mycelium will not try to bond with. And materials like wood or other organic materials often have contaminants in them that you're not aware of. So when it comes in contact with materials like wood, then you may find that you get some contamination in the mycelium that's usually what we call the greenies. There's some green contamination. There's which is a type of mold, usually called trichoderma, and there's other contaminations like bacteria that just make it so that the mycelium won't grow. But plastic is probably one of the best materials you can use, but other materials like stainless steel, they can be washed really easy, work just fine. But one of the huge advantages of plastic is that you can actually see through it to see the growth as it's going on. So using the vacuum former allows you to create any shape you want, but if the shape you want is a square or a circle, that might be easy enough to find just in a Tupperware container or a plastic container that's already made. So this is one of the weirdest shapes that we've made. It was for a group called Mars City Design, and it's an architectural model that would represent a much larger building that we hope to build with them. But you can see it's a little bit beat up. We've had everyone in the studio stand on this, including myself, and that was the ultimate weight test on this product. But yeah, you can get, whatever mold you make, you can fill, and you can get a interesting product at the end of the day. So now they're tightening up the frame so that the plastic stays in place. What they'll do is they'll unloosen the black pieces, and that'll enable them to raise it to the top. So that'll make it easy to slide along the pole. That'll go up, and there's 2 heating elements inside that metal box on the top that's now going to heat the plastic. And now we wait. We're waiting for the plastic to start to get hot enough that it sags, and then once we have the plastic sagging, we know it's ready to form to the table. Once that happens, we'll put our material on there, and we'll turn on the vacuum. So now it's starting to sag. Okay, and so we're going to turn on the vacuum. Drop it like it's hot. Okay. They're going to hold it there long enough for it to start to cool down. Meanwhile, Haley can use the board underneath there to kind of go around the edges to make sure it's tight to the edges. And we're done. So we can switch off both the vacuum and the heating elements. And then we'll remove. You can see it's made a really good fit to the mold. Does it cool down? All right. Now we'll just have to extract our wood block. And we have ourselves a mold. Even though this should be fairly clean, the first thing we're going to do is to sanitize this using some isopropyl alcohol. It's best to use 70% isopropyl alcohol. So we're going to wipe that down. So now we're going to put our gloves back on. We're going to wipe down the mold that we've just made. Again, using isopropyl alcohol. And then we're going to take our mycelium ready to grow and fill the form. You want to make sure you get it into all the corners, but you don't want to press too hard, or else it may stick to the form. So you just want to fill the form like that. And then what we'll do is we'll take a piece of plastic to cover that up to keep any contaminants from getting in.
Mycelium is going to continue to grow and it's going to like fit
Mm-hmm.
like this.
So the mycelium that's in there is going to regrow into the shape that we've just made. It'll get enough air exchange from the air pockets that are in between there, but we just cover that up with plastic, and then this is ready to be put on the shelf. It'll grow in place, and a couple weeks from now we'll have a tile. If we make hundreds of these, then we can have an entire wall.
A finished one.
So this is what that looks like after a couple weeks. You can see that the mycelium is now fully grown in there. It's going to continue to grow even after we take this out. But this is at a good phase right now that exposing it to air will start to dry it out. So it'll continue to grow as it dries, but we want the rest of the form, which is not quite as developed as the top, to look like the top. So what we're going to do is just transfer that over to another material. And unfortunately sometimes it sticks in the corners, but if you can get that out of there and allow that to heal itself over time. We're gonna set this out for another couple days, and then the rest of this form should look exactly like the bottom part of that did. And so a couple days from now we've made about 14, 15 of these, and so we'll be able to tessellate those into a pattern. So on to our brick making part. In Namibia, we have very large forms like the metal form you see here, and we have a press that's about 200 tons that actually forces the material into the form. Something like this that has a top and a bottom to it that we'll add into here. This part we don't highly recommend you try at home because we're going to be using a lot of force to actually deliver this in, but we want to demonstrate the process, and if you feel like you're handy enough to weld something like this, you can see the corners are reinforced. It's a very thick steel that we're working with here, but we're going to be putting a lot of force in here to actually compact the material into a brick. So first thing we're going to do is get the bandsaw back. We're going to pick out one of our bags of reishi that's ready to harvest, and we're going to harvest the top part of that, and actually we're going to cut the mycelium to fit into the form. So Haley's going to make several cuts, seeing that it fits into the form well, and then we're going to load the form and take it to the press. So it's ideal if it fits perfectly into the form. So you can see here we have a corner missing, but that still won't affect our brick too much because we're going to be compacting it. The material will move around quite a bit and fill the cavity. So the first thing we're going to do is we're going to set the bottom to our press, to our mold. That's just going to slip right in there. Then we're going to put in a sheet of Mylar. These are reusable sheets that are fine to go in the oven. This will keep it from sticking to the metal on the bottom. Then the material goes in. A perfect fit. Mylar again. And then the top. So we're going to take this to the press. The press is going to push this down, and then we'll be able to include these pins to go across there, which will hold the plate in place. When we take that to the oven, then that will be baked under pressure. And so once it's dried out, it'll be a smaller, more compact, very dense, very strong, insulative brick made from mycelium. So Haley is going to bring our brick mold and our material and put it onto this H-frame here. So this is a H-frame press that is 30 tons, and it will be compacting the material inside the metal form. We will pin that into place and then put that into the oven. So now the brick is held into place by the pins. It's under pressure now, and it can go into the oven and bake this way. And so when it comes out of the oven, we'll have a solid brick that is compacted and has it can be structural, insulative, fire resistant, sound attenuating, and very heavy. Thank you, Haley. Haley and Armando are unloading the oven now. These have been in there overnight. They've cooked for about 24 hours. And they went from a moisture content of about 60% now down to about 10%. That's what gives the material its strength. By the dehydration of the material and the compaction of the material, it's now a very strong material. Okay. All right, so we're gonna pop the pins out first. Flip it over. So the compression strength of the Myco block is 26 megapascals, and that compares to the concrete block, which is 12 megapascals. So the compression strength is the main thing that you need for walls that are bearing walls, or in the case of the BioHab, an arched wall, because all of the members of all the blocks in the arch are going to be in compression. But one other important thing is the ability to resist impact, and we'll see here that the comparison of our material versus a concrete block. Armando is going to show you the difference in the impact resistance of our material over a concrete block. Once again, this is Chris Maurer from Redhouse Studio, thanking you for spending some time with us today. We learned about growing mushrooms, we learned what we can do with the waste from the mushroom cultivation, and we learned what biomaterials can do throughout the planet. If you want to learn more, visit us at www.biohab.org. Thanks again.